The people of ancient times saw only beauty in the stars and filled the heavens with fanciful and lovely names. Berenices, Aldebaran, Lyra, Rigel, Andromeda, Draconis, Taurus, and Libra. Today we know that space is a violent, vicious place, black and frigid beyond imagining, devoid of all that can sustain life, a killer, an enormous, endless, boundless nothingness that seems to say to man, you shall not pass. Despite this, man will penetrate the far reaches of the dark beyond. But to do it, he must first know more about space. Knowledge precedes conquest. One of man's most valuable tools for studying space is the satellite. Those bizarre-shaped objects that rockets blast into space to orbit the Earth more or less indefinitely, continuously radioing data back to Earth. This is a model of one of the more recent satellites to be launched, Ariel I, built jointly by the Americans and British in history's first cooperative space venture. Mission of the Ariel I? To discover more about the ionosphere, that vast canopy of ions and free electrons that starts about 50 miles above the Earth's surface and extends out for at least 2,000 miles. The ionosphere, you recall, prevents radio waves from getting lost in space by reflecting them back toward the Earth. By thus making possible long-range radio, telephone, and telegraph communications, the ionosphere has tremendous practical value. So we want to learn everything we can about it, particularly how to predict the so-called ionosphere storms that can interfere with communications over the entire sunlit half of the globe. Thus, in 1959, British and American scientists decided to team up and build a sophisticated ionosphere satellite, Ariel I. Under the guidance of England's famed Royal Academy, the instruments were designed and built by scientists from the University of Birmingham, Imperial College London, the University of Leicester, and University College London. To explain the satellite's scientific instrumentation, here is Dr. Peter Wilmore of University College.
The ionosphere is composed of electrons and positive ions. All of the aerial experiments, except one, the cosmic ray experiment, are designed to study either the electrons or the positive ions of the ionosphere. We started out by asking ourselves certain simple questions. What is the electron temperature in the ionosphere? And two of the probes on the satellite measure electron temperature. What is the positive ion temperature? Another of the probes measures this. In particular, we're interested to know whether these two temperatures are the same. Then, how dense is the ionosphere? Two of the probes measure the number density of the electrons by methods which are quite different in principle, so that we can obtain a cross-check between the two measurements. Another probe is a mass spectrometer, which measures the mass of the positive ions, and from this we can identify them. We can also tell whether the ionosphere is in equilibrium. If this is the case, we expect to find heavy ions, such as those of oxygen, at the bottom of the ionosphere, and light ions, such as helium plus and hydrogen plus, should float to the top. The ionosphere is largely produced by sunlight, not the visible light, which enables us to see, but the shortwave ultraviolet light and X-rays. So we need to know more about the sun as well as the ionosphere, since they are so closely related. Two of the experiments measure the intensity of a line in the ultraviolet spectrum of the sun, the Lyman alpha line of hydrogen, as well as measuring the intensity of the X-rays. The remaining experiment is to study the cosmic rays which bombard the Earth from great distances. This uses a Cherenkov detector which divides the cosmic rays into heavy particles and light particles. Now, in addition, the Earth acts as a huge magnet. When the satellite is over the equator, only the most energetic cosmic rays are able to penetrate the magnetic field and reach it, whilst the less energetic cosmic rays are deflected by the field and reach the satellite when it is at high latitudes. By studying the variation in cosmic ray intensity at different latitudes, we hope to learn more about conditions in interplanetary space, the region between the Earth and the Sun. There are 3 chambers on this side of the satellite which are sensitive to the Lyman alpha light emitted by the Sun. On the other side, there are 2 X-ray gauges which measure the intensity of the X-rays. This sphere on the front of the satellite is the positive ion mass spectrometer. This dome contains the cosmic ray Cherenkov detector, whilst the sensors for measuring the density and the temperature of the electrons are at the extremities of these 2 booms.
Features of Ariel I structure and design are described by the project coordinator, Goddard's John T. Shea.
The satellite is 23 inches in diameter and weighs 133 pounds. The structural materials are principally fiberglass and aluminum. The central body is an epoxy-bonded and riveted monofilament wound fiberglass cylinder with a density of 0.071 pounds per cubic inch. The upper dome is 1/16 inch thick. The lower dome is 1/32 inch thick. The upper dome and midskin are bonded and riveted to aluminum rings. Beneath the main shelf, 2 aluminum struts support the booms. 4 struts support the solar paddles. A major problem is to prevent excessive heat from entering the satellite when it is orbiting in sunlight, while simultaneously preventing an excessive heat from escaping from the satellite interior when it is orbiting in darkness. Thus, the satellite is covered with a number of thermal coatings, plus a coating of copper to serve as a ground plane for the antennas and prevent RF energy from reaching the internal electronics. The coatings are sealing varnish, lacquer, conducting silver paint, electroplated copper lacquer, evaporated gold, and stripes of black paint. The white stripes were added for a final thermal trim. The gold coat is used because it best fits the scientific requirements that the satellite's top coat be conductive while having good reflective qualities. The satellite's electrical needs are supplied by the approximately 10-watt, 15-volt output of the solar paddles. The paddles are 1 foot by 1 1/4 feet, covered on both sides with flat-mounted, high-efficiency selenium cells. When orbiting in sunlight, paddle output drives the satellite's electronics and charges the batteries. At other times, the batteries take over. These batteries are nickel-cadmium sintered plate types in stainless steel cases. Capacity is 6 ampere hours at 12 volts. Since Ariel I will have done its job after being aloft for a year, a timer will turn off the power supply at the end of that period. This will prevent cluttering up the airwaves with useless transmissions. Ariel I's telemetry, produced at Goddard, is the last word in efficient modular design. It handles 500,000 bits of information a day. The 2 encoders accept the outputs from the transducers of the various instruments and produce a frequency proportional to these outputs. The output of the high-speed encoder is constantly transmitted to Earth in the form of a sequential series of 10 millisecond pulses. The low-speed encoder output is tape recorded for a complete orbit, then on command from the ground is transmitted in a 2-minute burst. By using 2 encoders in this manner, more complete reception of data is assured. The tape recorder is 3 inches in height by 7 inches in diameter and weighs only 36 ounces. It is a prime example of the remarkable miniaturization of Ariel I. The transmitter is used for data transmission and as a signal source for the tracking of the satellite by ground stations. The frequency is 136.410 megacycles. The signal is phase modulated with an output power to the antenna of 250 milliwatts. The receiver operates on the standard NASA command frequency. The antennas are cross-dipole arrays. They're fed by a coaxial hybrid cable that isolates the transmitter from the receiver. The radiation pattern is omnidirectional with circular polarization of opposite sense off the vertical spin axis and linear polarization in the plane of the turnstiles. As an example of what imaginative design can do, the UK1 electronics use 1,000 transistors, yet requires the equivalent power output of just 1 flashlight cell.
With the satellite completed, engineers began a series of rugged tests to prove Ariel's ability to perform under the tremendous stresses of the rocket launch and orbit. First, was the satellite in balance? After mounting and trial spin, weights were added to acquire optimum balance. To maintain stability in space, the spinning satellite must be in near perfect balance. These tolerances were demanding. The spacecraft's spin axis must be offset from the principal axis by no more than 5/1000ths of an inch. The tilt relationship of these axes could not differ by more than 8/1000ths of a radian. Next came tests inside NASA Langley's 60-foot vacuum sphere. Here, the deployment of booms and paddles and the release of the yo-yo were checked out under simulated space conditions by NASA engineers and technicians. High-speed photography recorded the action. Ariel's mechanical operations functioned properly. The yo-yo device consists of 2 close-wound extension springs extending 1/2 turn around the satellite's midskin. Relatively heavy weights are fastened to one end of each cable. After the satellite's 3rd stage combination is detached from the rocket's 2nd stage, it is given a stabilizing spin of 160 RPM. The yo-yo reduces the satellite's rotation to about 70 RPM. The spring-type yo-yo compensates for errors in spin rate and moment of inertia. The destructive force of vibration. How would Ariel withstand it? During testing, input vibration was controlled by 1 accelerometer. 2 others monitored lateral crosstalk. Instruments at 14 critical locations measured the resulting transmitted vibration levels, while signals from the 3 input accelerometers recorded the sinusoidal excitations. During the random vibration tests, signals were passed through a bandpass filter-type analyzer adjusted to scan the test spectrum in the applicable test duration time. Gaussian random vibration was applied with G-peaks clipped at 3 times the root mean square acceleration. Then, in this giant centrifuge, Ariel was subjected to 25.4 G's simulated flight acceleration force. In a thermal test chamber, Ariel I was exposed to the extreme temperature variations it would encounter in orbital flight, blistering sunlight, and the frigid darkness of the Earth's shadow. The test chamber was first evacuated to a pressure of 1 × 10⁻⁵ torr. Satellite temperature was then lowered to -10 degrees centigrade, 10 degrees lower than expected flight values. For 3 days, it was operated at this level. During the 3-day high temperature test, Ariel was operated at +50 degrees centigrade. During the solar simulation test, the walls of the test chamber were cooled to -60 degrees centigrade and radiant energy applied to the satellite in chosen aspect angles. The overall result from these tests proved that Ariel was ready for pre-flight calibration. Meanwhile, components, including solar panels, designed to supply power to Ariel in orbit, underwent continuous development and testing. In actual flight use, the solar array would be controlled to a continuous output of from 1/2 to 2 watts. Now at Cape Canaveral, Ariel was ready for a final series of pre-launch field calibrations. Antenna test patterns were made, and the electron density experiment underwent final calibration. Then, Ariel was mated to the separation device and Delta launch vehicle's solid propellant 3rd stage. The entire assembly was dynamically balanced and weighted to ensure Ariel's stability while being launched into its 18,000-mile-an-hour orbit of the Earth. Testing completed, the satellite's 3rd stage assembly is married to the 2nd stage of the Delta launch vehicle. English scientists made a final check of their instruments. The moment had come. Men and machines cleared the launch area. Inside the blockhouse, personnel were busy with final pre-launch activities. Men and instruments were ready. Together, American and British scientists, engineers, and technicians were at the culmination of 2 years' work. April 26, 1962. The time, 1 p.m. The event, man's first international orbital exploration of space. The countdown.
6, 5, 4, 3, 2, 1, 0.
The launch was perfect. Ariel I followed the planned launch sequence without a hitch. Ejection of nose cone. 2nd stage burnout. 2nd and 3rd stage coast and yaw until the peak of the ascent path was reached and the rocket was in its proper attitude. Spin up of the 3rd stage to about 160 RPM for stability. 2nd stage separation and firing of retro rockets. Ignition of 3rd stage. Burnout of 3rd stage. Coast to allow 3rd stage thrust to cease. Release of yo-yo and slowing down to 3rd stage in satellite combination to about 70 RPM. erection of booms and resulting slowdown to about 47 RPM. Erection of solar paddles and reduction of satellite spin to about 35 RPM. And finally, separation of the satellite from the third stage at a differential velocity of 7 feet per second. The successful launch began a big new chapter in the Ariel I story. Now, Ariel I had to be constantly tracked, and the data it was transmitting, received, decoded, and interpreted. Tracking the satellite was the job of NASA's Minitrack network, a vast system of radio ground stations located throughout the world. Tracking is accomplished by radio interferometer or phase comparison techniques using a continuous radio signal from the satellite received at pairs of ground antennas. The antennas are separated by a known distance and wavelengths equal to the satellite signal. By measuring the relative difference of signals arriving between two antennas, the direction angle to the satellite can be determined in one plane. A similar measurement by antennas placed perpendicular to the first pair establishes the position of the satellite relative to a second plane. The combination of these two measurements produces the position of the satellite in orbit. Tracking antennas are pedestal-mounted slot type with ground screens. They are accurately positioned geographically and precisely leveled. Minitrack data acquisition antennas are 9-element grouped arrays on 10-foot towers. They use a remotely controlled azimuth and elevation drive system. A separate antenna transmits signals to the satellite, commanding it to perform certain functions, such as relaying its stored data. The data acquisition receivers are triple conversion superhets tunable in 1 kilocycle steps over the 136 to 137 megacycle band. Data from the satellite is taped on 7-track Ampex units using 1/2-inch tape. Direct, FM, or PWM data can be received. Tapes from the Minitrack stations are then forwarded to Goddard Space Flight Center. Here, Goddard technicians check and edit each tape for its usefulness and quality. Data format is then changed from analog to digital. As new tapes are completed, they are sent to Great Britain for analysis by scientists of the Royal Society. Ariel I, the first international satellite, a joint effort of scientists of Great Britain and the United States, helping man acquire the knowledge he must have to master the dark beyond.